The Poisson Process, a dangerous bend optional segment. Thinking of the Poisson in terms of arrivals leads to a very natural time-varying phenomenon. So imagine that starting time at time 0 and progressing to the right, we see points arriving roughly in accordance with a Poisson distribution. The number of arrivals then in a certain amount of time should constitute an arrival process. This is what we want to try to model. A Poisson process, let's call it n, as a function of a continuous time parameter t, ranging over the positive half line, of a given rate, also called the intensity. Let's use the Greek letter alpha for this. Alpha represents, in this kind of picture, the number of arrivals per second on average. So, a Poisson process of rate or intensity alpha is governed by a particular probabilistic structure. Let's begin by looking at how we interpret n of t. Pick any point in time t and look at the time period from 0 to t. Then there are a certain number of arrivals in that time period. Of course, this constitutes a chance variable. So we think of n of t as the number of arrivals up till that time t. Now, if you tell me what the number of arrivals is at all points in time t, then in any given interval we can determine how many arrivals were there in that interval. Let's abuse notation just a little to write down our understanding of what happens inside an interval. So let us pick a given interval, let's say from s to t. Now, the number of arrivals in this interval, let's call this n of the interval s to t, is exactly, of course, the total number of arrivals up to t, from which you take away the number of arrivals up to s. Good. Naturally, we'll want these basic chance variables to have a Poisson formulation. So this comes up next. What is the key characteristic of a Poisson process? First, we require that in any interval, let's say s comma t, where s and t are arbitrary positive real numbers, s being less than t, the number of arrivals is a chance variable n of s comma t, which is Poisson distributed with a parameter alpha times the length of that interval, alpha times t minus s. Let's pause to make sure we understand what's going on here. Remember, the expectation of a Poisson variable is its parameter. So if you tell me that in an interval of length t minus s, the Poisson variable has got parameter alpha times t minus s, then on a per length basis, the expected number of arrivals is alpha. But that's exactly how what he had in mind when he talked about alpha as the rate of arrivals, the intensity of the process. Okay, but this is not going to be enough. In addition, we demand that if we look at non-overlapping intervals, disjoint intervals, then the arrivals in each of them constitute independent trials. In other words, prior arrivals do not affect subsequent arrivals. So this is the underlying independence characterization of the Poisson process. So a time-varying chance-dependent function, n of t, which has got this probabilistic infrastructure. In any interval, the number of arrivals is a chance variable, which is Poisson, with a parameter which is proportional to the length of the interval, and with a property that the arrivals in disjoint, non-overlapping intervals are independent. Such a process is called a Poisson process. Of course, at the back of our mind, we have in mind applications like the following. People arriving in a queue over a certain period of time. The number of arrivals, as we track them, follows a Poisson process very roughly. packets arriving at an internet router, traffic arriving at an intersection. If one wants to visualize this, we can plot n of t versus time, and then we get a graph in time. What kind of graph would this be? Well, n of t is a number, and therefore you're going to start at 0, and every time there's an arrival, n of t will increment by 1 unit. Such a process is sometimes called a counting process. And so here are examples of n of t generated when the rate alpha I've chosen for visualization purposes to be 1. And here are 3 kinds of curves that arose by random generations of random arrival points. Now, we should pause and see if we can flesh out the statistical structure, the probabilistic structure, a little bit more. Of course, this is much more complex than anything we've considered hitherto. Here, we have not just 1 or 2 or a finite number of chance variables, but chance variables over an entire continuum. And among other things, we should ask, are things defined in a consistent way? So let's take a look at this process again and tease out some more probabilistic intuition. So again, the key characteristics of a Poisson process is that in any interval, the number of arrivals is Poisson with a parameter, with an expectation proportional to the length of the interval. And furthermore, arrivals in non-overlapping intervals are independent trials. So in particular, if you give me an interval from, say, S to t, the number of arrivals in that interval, n of S of t, in compact notation, is itself a Poisson variable with a mean, with an expectation, alpha times t minus s. If we set s equal to 0, then we are dealing with the interval from 0 to t, and we're looking at the number of arrivals from 0 to t, but that, of course, is what we call the original process, n of t. And therefore, n of t itself, for any given t, is Poisson with a parameter alpha times t. If the mean arrival rate is alpha arrivals per second, then in a window of time t, the number of arrivals on average is going to be alpha times t. Now, let's take an interval from 0 to t and see how the independent increment process is turned into account. So take an interval from 0 to t, and let's say we partition it into n subintervals, call 0 t sub 0, and then think of a sequence of values t1, t2, t3, culminating in tn, which is t. So this appears on your screen. Now, what we've done is taken an interval from 0 to t and partitioned it into n non-overlapping subintervals. t0 to t1, t1 to t2, t2 to t3, and so forth. How many arrivals are there from 0 to t? Well, that is exactly n of t, right? Well, the number of arrivals in that whole interval is precisely the sum of the arrivals in each of these non-overlapping subintervals. And therefore, we have an identity. The number of arrivals from 0 to t is the number of arrivals in the first subinterval, added to the number of arrivals in the second subinterval, and so on down to the nth subinterval. Now, pause for a moment, right? On the left of your expression, you've got a variable which we know by the definition of the Poisson process should be Poisson with parameter alpha times t. But we have an identity. On the right, we have a sum of n quantities. Each of those quantities represents a Poisson variable, a Poisson number of arrivals in a given subinterval. What do we know about them? Well, they're individually Poisson. Each of them has got a parameter proportional to the length of that subinterval. So, n of t0, t1 is Poisson with parameter alpha times t1 minus t0. n of t1, t2 is Poisson with parameter alpha times t2 minus t1, and so on. But we know more. The independent increment property posits that each of these is an independent trial. these are independent variables. And so what we're doing is to stitch together a number of arrivals up to t, we are adding independent Poisson variables. Aha! But our slogan for the stability of the Poisson tells us that if we add n independent Poisson variables, the result is Poisson and its parameter is the sum of the individual parameters. Let's quickly check. Identify lambda 1 with alpha times t1 minus t0. Identify lambda 2 with alpha times t2 minus t1, and so on. And now we've got a long expression. And you look at this and you realize, oh, wait a minute, this thing telescopes beautifully. For example, you have t1 contributed by lambda 1, and you have minus t1 contributed by lambda 2. They cancel. t2 contributed by lambda 2 and minus t2 contributed by lambda 3. They cancel. And in fact, all subsequent terms cancel, leaving only the bookend terms, t0 and tn. And therefore, this entire sum of the Poisson parameters becomes simply alpha times tn minus t0. But recall, tn was t, t0 is 0, and therefore this is exactly alpha times t. Exactly as we should, because the result of adding these independent Poisson streams is exactly the number of arrivals up to t, and that should be Poisson with mean alpha times t. This independence stability property of the Poisson, then, is at the heart of the Poisson process. At this stage, it looks promising. We now got a mechanism for describing congestion phenomena, traffic phenomena, queues. But the listener might well quibble and say, this sounds very good, but oh dearie me, this is really complex. And she might well ask, well, look, what is the probability space under question? What is the underlying sample space? It's not at all clear in the way we've described it so far. So our next dangerous bend optional segment comes to the question of, given a Poisson process, what is the underlying probability space, the sample space that fuels such a process? And this will lead us to the discovery of an exponential distribution and various distributions connected with the theory of waiting times and queues. This comes up next.